Hello and welcome back. This is episode 3 of quantum mechanics. So far, we have looked at the fundamentals of why quantum mechanics exists. We looked at how classical physics starts failing at a minute atomic levels, and we also looked at a little bit of what quantum physics is. So today we are going to look into quanta. We're going to look into Planck's constant. We're going to look at blackbody radiation. So all of those fundamental concepts that really make quantum mechanics the most useful thing. So let's get started. If you have not subscribed to this channel, please do subscribe. Look at my previous episodes if you have not started the journey on quantum mechanics. So with that said, let's get started. For a long time, physics believed it understood heat and light. So when an object was heated, it became hotter. When it became hotter, it glowed. And as it glowed more intensely, its color shifted from a dull red to orange, yellow, white. So this behavior was universal. Every heated object followed the same pattern, whether it was a metal rod or molten lava or the surface of a star. Everything about this process also felt smooth and continuous. The color changes are continuous. Nothing appeared to jump. And so, almost without discussion, physics made a very quiet assumption that seemed perfectly reasonable. It assumed that energy flows continuously. So this assumption matched everyday experiences. It worked in mechanics, fluids, sound, classical electromagnetism, in a lot of places. And for decades, it appeared like it was perfect. But then, physics tried to explain thermal light in detail. So this is where the assumption revealed a fatal flaw. So let's look at that, heating an object in the classical view. So according to classical physics, a few things start failing. So let's imagine holding a metal rod over a burner. At first the rod remains dark. You can feel heat spreading through it. There is no visible glow, but you can feel the heat in your hand. As the flame grows stronger, the rod begins to emit a faint red light. That's red hot. You increase the heat further and the glow intensifies, shifting through orange, yellow and white hot. Of course, you can't hold it at that temperature. So at very high temperature, the rod becomes really white hot. So before quantum theory, physicists explained this behavior using classical ideas. Heat was understood as energy of motion. Atoms were thought to vibrate more violently as temperature increases. So within matter, there were also electric charges, and classical electromagnetism taught that any accelerating charge emits electromagnetic radiation. So you are heating this object, atoms are vibrating violently, and then the electric charges are moving around. So according to magnetism, accelerating charges emits electromagnetic radiation. So that's how you start seeing light being emitted. So putting this all together, the explanation was straightforward. Heating increases motion. Faster motion means faster oscillation. Faster oscillation produces higher frequency light. So it was an elegant picture and almost entirely correct. So the assumption that no one questioned was this. Hidden inside the classical explanation was an assumption so natural that it went almost unnoticed. So the assumption was energy could be divided endlessly. You can have any quantity of energy. Classical physics allowed energy to be transferred in arbitrarily small amounts. So if a charge could vibrate, it could vibrate with any amplitude. If it emitted light, it could emit any tiny fraction of energy. There was no smallest unit, no minimum step. So using these assumptions, physicists calculated how much light a hot object should emit at each frequency. So the mathematics kind of followed nicely and cleanly, but the final result was shocking. At higher frequencies, especially in the ultraviolet range, the predicted energy output grew without limit. According to classical physics, even a moderately warm or hot object should emit infinite energy. So just to explain this a little more, if you take a rod, if you are heating it, the way the energy is calculated is based on the number of electromagnetic modes that are there in the rod. So for every given frequency, you can have a certain amount of, let us say, standing waves inside that. So as the frequency increases, you have shorter and shorter wavelength, which basically increases the number of modes you can accommodate inside the same object or same place. So eventually, by the time you hit ultraviolet wavelength, you are literally hitting unlimited energy, because there are unlimited modes possible. So that led to something called as the ultraviolet catastrophe. So this is the observed conclusion which came to be known as the ultraviolet catastrophe. So if we go according to classical physics, the more you heat an object, as you hit the ultraviolet range, you're going to have unlimited energy coming out of it. Nature, of course, refused to behave catastrophically. Experiment showed a very different reality. Radiation increased with frequency, that's correct. It reached a peak and then fell off sharply. Where we were expecting the catastrophe to happen, it actually fell off sharply. High frequency light was naturally suppressed. So the equation was correct, the reasoning was sound, but the assumptions we had made was wrong. So this is where Max Planck comes in. Max Planck did not set out to overthrow classical physics. He trusted it deeply and he believed nature was fundamentally continuous. So for years he tried to fix the blackbody problem without abandoning that belief. Eventually, out of desperation, he introduced a single radical assumption, which he initially regarded as nothing more than a mathematical tweak. He proposed that energy is not exchanged smoothly. Instead, energy is exchanged in discrete packets, which he called as quanta. Each packet, he suggested, carries an energy proportional to the frequency of the radiation. So, this is the formula E is equal to hv. The equation did not describe the total energy or average energy. It describes the energy of one indivisible exchange or one packet. So E is equal to hv. Basically, the constant h is known as the Planck's constant. It has a very small value, which you can see on the screen. It is an extraordinarily small number, so small that in everyday life we never notice its effects. It is so small that the world appears smooth and continuous to our senses, but at a minuscule level, you can see that it has a value. So just by adding the constant into the formula, what you get is a small step. So every time you try to increase the size of the you try to increase the frequency, the size of the packet also jumps by a particular multiple. That is Planck's constant. So the number kind of changes everything. With this single assumption, the blackbody problem vanished instantly. Now let's take a look at Planck's radical fix. Planck made one single change. He assumed that energy is not continuous. Instead, energy can only be exchanged in discrete packets or quanta. He proposed E is equal to hv. This means higher frequency needs larger energy packets. So as the frequency increases, the energy packet that is held is going to be much larger. So you can't give a system half a packet. So either you give full quantum or nothing. So as you go towards ultraviolet band, the size of the energy packet is so large that you can't give it that much energy at all. So the radiation kind of drops. So that is Planck's fix for the whole problem. So the predicted radiation curve matched experiments perfectly. No infinite energies, no adjustments, everything worked. So physics had crossed a boundary it could never retreat from. So let's look at what quantum really means. The word quantum does not mean some strange mystery or magic. It means a fixed amount. Energy could no longer be divided endlessly. It had to be exchanged in whole units. So Planck's constant makes sure that energy is always a whole unit. You could have one packet, 10 packet, million packets, but you can never have half a packet. So this was not a limitation of measurement or technology. It was a statement about how nature itself works. So in Planck's equation, the packet size is not the constant alone. The packet size is the product of the constant and the frequency. So Planck's constant sets the scale and frequency determines how large each packet is. So as frequency increases, the packet size also increases. So let's look at red light. Red light corresponds to small energy packets. Blue light corresponds to larger ones. Ultraviolet light requires very large packets. So this simple fact explains why high frequency radiation is very rare. So let's walk through this experiment of heating a metal rod in more detail. So imagine a steel rod held over a gas burner. At first, the rod is dark. You feel heat, but you don't see anything. A little hotter, the rod starts glowing dull red. Hotter still, it becomes bright red, then orange. Extremely hot, it turns white hot. So this sequence is universal. Every heated object behaves this way. The question is, why does the color change in this order? So to understand that, we need to go one more step into what is happening inside the rod. Inside the rod, atoms are vibrating, electrons are shaking, charges are oscillating. So heat is basically a lot of jumping or jiggling energy. As the burner supplies energy, vibrations get stronger, oscillations get faster. Faster vibration, higher frequency light. So far, this matches classical thinking. But classical physics assumed that energy can be released in any amount, even very tiny bits. So it predicted as temperature rises, atom would emit all colors, including huge amounts of ultraviolet with no upper limit, which would basically mean that the rod would start blasting dangerous UV light even at modest temperatures. But that doesn't happen. So something limits which colors appear. Planck's key idea applied to the rod. Planck said atoms can only give off energy in fixed packet. The packet size depends on color. Red light, it gives off small packets of energy. Blue light, it gives off bigger packets of energy. Ultraviolet light, then it has to give off very big packets. So each color requires a minimum payment. You can't emit blue light unless you can afford a blue sized packet first. So given a certain amount of energy, can you really afford to emit blue light? Do you have that kind of a packet available? Unfortunately, no. By the time you get to ultraviolet, it's just not possible. It's just too much of energy or too big a packet size that is required. So let's also look at why the rod glows red first. At low temperatures, atoms have limited energy. They can only afford small packets. So red light appears first. Higher colors remain dark. Turning up the burner. As you turn up the heat, atoms gain more energy, bigger packets become affordable. So now the rod can start emitting orange, yellow, and eventually blue. But remember, each steps requires more energy per packet. So to emit any of the higher frequency colors, you need a much bigger sized packet. So why ultraviolet is very rare? So ultraviolet packets are huge. Even at high temperatures, most atoms still cannot afford a packet of that size. So UV emission remains very weak. So this naturally prevents infinite energy, and the ultraviolet catastrophe is also avoided. So this is how Planck's theory kind of explains packet size and how it helps. So Planck said energy packet size grows with frequency. Translated into everyday language, low frequency light is cheap packets, high frequency light is expensive large packets. So as color shifts from red to blue to UV, each step up demands a much larger chunk of energy. Eventually, the chunks become so large that almost no atoms can pay. That's why emission drops off. The too big to pay effect, that is the key insight. At some point, packet size becomes extremely large than the energy available. Emission simply stops. Not because nature forbids it, but because it's energetically impractical. This is how nature forces a limit. When a solid object is heated, energy does not pour into a single atom or electron. Instead, it is distributed across trillions of atoms into different quantum modes. Most thermal energy goes into vibration of atoms in the lattice. So when you heat a particular object, the thermal energy is taken up by the vibration of atoms in the lattice. Motions that are themselves quantized, by the way. So some energy also goes into electronic excitations, where the electrons occupy higher allowed states. Accelerating charges naturally radiate energy away from that. So when we say an atom is excited, we do not mean electrons physically oscillate across orbits like planets, and electrons do not move that way. It's not that they are going to move faster. So when we say that they exist as quantum states, you can think of it as standing wave patterns with fixed energies. Higher excitation simply means occupying a higher allowed state. There is nothing continuous in between. It's very abstract to just go through this. So you can think of this as some kind of a cloud or a electron cloud which exists around the nucleus. So that is one state. So when the electron tries to move to the next state, it is basically expanding the size of the electron cloud into something much bigger, and it now is going to stay in that quantum state. So it keeps going in particular discrete steps. There is no in between steps. So let's look at why high frequency light is rare. To emit light, a system must lose energy. So in quantum terms, it drops from one allowed state to a lower one, and the energy difference becomes a single photon. So the photon must carry exactly the energy dictated by Planck's rule. High frequency photons carry large energy drops. Such drops are allowed, but they are rare. Heating does not lift atoms smoothly upward, it nudges them randomly step by step. So most atoms reach low or moderate energy states and emit red or yellow light. Very few reach the extremely high states required to emit ultraviolet light. High frequency emission fades naturally not because it is forbidden, but because it is statistically unlikely to happen. So why energy cannot be pulled? A natural question arises, why can't many atoms combine their energy to produce one large packet? Quantum mechanics does not allow that. Energy is stored locally in quantized states. A photon is produced by one transition, and one transition produces one packet. There is no shared reservoir, no collective payments, no way to pool energy. One other thing, frequency and brightness are not the same. So it is important to separate the two ideas that we often get confused by that. The frequency of light, its color, is determined by the size of the single energy transition. The brightness of light is determined by how many such transitions occur. Repeating the same transition makes light brighter, not bluer. An electron is not restricted to dropping only to the nearest level, it may drop across multiple allowed levels. But the frequency always reflects the total difference or total energy difference of a single drop. So finally, let's look at the role of Planck's constant. Planck's constant does not vary, it sets the size of energy steps and the scale of the quantum effects. It defines the boundary between smooth appearances and discrete reality. If Planck's constant was 0, energy would be continuous. If Planck's constant was 1, energy would be continuous and classical physics would return with all its contradictions. If it were much larger, even visible light would be rare to find. So our universe kind of sits at a very precise quantum resolution. So at human scales, quantum steps are tiny. The staircase looks like a smooth ramp, but at atomic scales, the steps kind of dominate. So this is kind of the quiet birth of quantum physics. Planck did not yet speak of photons. He did not reject classical physics. He believed he had found a very clever workaround. But nature had something even deeper. Energy itself is quantized. So from this insight, we would follow into photons, atomic stability, quantum mechanics, modern technology, a lot of things. So quantum theory was not born from imagination or philosophy. It was forced into existence by a very stubborn experiment and an impossible infinity problem. Energy kind of did not flow, but it jumped in steps. And in these jumps, the true structure of reality quietly revealed itself. So that's a fairly dense episode. If you are completely new to quantum physics, take some time, go back and check out some textbooks or maybe some material on the web. Get a good understanding of this foundational part of quantum physics, and then we can move on to the next episode. So, meanwhile, keep learning. Please do subscribe if you like the episode, hit the like button, and come back for the next episode. Thank you.